This is a series of videos that's going to be looking at group theory, introducing definitions of that and looking at results that follow from that. Now, I want to start this video specifically is going to be focused on the building blocks which make up groups and not sets and binary operations. Both these things are going to be things you've come across before, but I want to introduce some terminology, look at some examples, introduce some vocabulary and how we might classify different properties of both these things. So set theory is something you can do in loads of detail at undergraduate and beyond. At the moment, the only thing I want to consider a set as is a collection of elements. And I should say a well-defined collection of elements, because if we really want, we can make things that lead to paradoxes. But I'm going to approach this by thinking that we're not deliberately setting out to try and break this. So if a set is a collection of elements, then there's a few ways we can define a set. If we have a finite number of elements in our set, we can just list them. So one way I could define the set is just by, we'll always do a set with curly brackets. My curly brackets aren't very good. You might be able to do better. But if I want to do a set containing the elements 1, 3, 4, 7, and that's all I want, then I could just do that, comma between each element, and curly brackets each end. I will never have a repeated element in the set, so I wouldn't put a 3 in again. That wouldn't change it because the set either has the element 3 in or it doesn't. So this is a set with 4 elements. That's an example of a finite set because there's a finite number of elements there. That's about as simple as we're going to get when it comes to looking at sets, just being given something with this is the list. Next most complicated we could have, it's still a finite set, would be one where they're described, but you're not given a list as such. So I could give you the set that says n, and then when we write a colon, this is going to say such that. So I'm saying, no, I want all numbers n such that n is a 2-digit prime number. Now, we could rewrite this out as the list of all the ones. So 11, 13, 17, 19, and so on. I'm not going to try to say them all because I'm sure I'll get one wrong. But you could list them all out. But this is a quicker way of doing that because you don't have to write them all out. And there's still a well-defined list of elements we've got there. Now, those are both examples of finite sets here. But we'll also work with infinite sets, and actually most of the sets you'll work with are probably infinite sets. That's to say that there's an infinite number of elements in there. So a few common examples of infinite sets. Well, and there's notations that go along with these. One would be all integers. So, and if you want notation here, it says z, and we have this weird double line through the z here. So this is all integers. That's obviously an example of an infinite set because there's an infinite number of integers. Note that does include negatives and it does include zeros. So negative 2 is an integer, 0 is an integer, so we can go in both directions infinitely. We could have Q, which represents the rational numbers. And when I'm saying the rational numbers here, this is saying any number that can be represented as a fraction with an integer over an integer. So if we wanted to represent this with a more clear definition rather than just saying this like we did with the set of 2-digit prime numbers, we could say this is numbers of the form a over b, where, sorry, I should have a such that there. So colon to say such that. So we want two things. We want a and b to be integers. So that's what we're saying there. And there's one other thing we need here, which is we can't have b being equal to 0, because if b was 0, a over b would be undefined. So we can put that in there. So that's an alternative way of writing the rational numbers rather than writing q. Some others, though, we might have. If you see r, and you'll see with all of these notations, there's always a double line when we're writing these sets. This is all the real numbers. So this includes irrational numbers, it includes root 2, it includes pi. So this is any number you can think of, ignoring complex numbers and ignoring quaternions if you know about those. The next one we might mention is the complex numbers. This is a C just with a line through, so you should at this point, be happy knowing what complex numbers are. If you wanted to write this as in our other set notation, you could say it's of the form a plus bi such that a and b are both real numbers. So this, my pen's just playing up there. Let's try that. There we go. So that's one option there. Now, this symbol here, sorry, I should have mentioned that up here as well. This symbol here is just saying is a member of. So that's saying A and B are members of integers for the rationals, and the other one saying A and B are real numbers. The only other couple of notations you need to know, if you see an n with a line through, this is the natural numbers, and that's another way of saying the counting numbers or the positive integers. So that in some conventions, people start from 0, but the most common convention, the one we're going to work with, is starting from 1. So that's just the numbers 1, 2, 3, 4, 5, 6, and so on. So as I say, the positive integers. And the final one I want to mention, which isn't an infinite set, in fact, it's the smallest that we can have, is this. It's not a Greek symbol, it's a Norwegian symbol, but this is the empty set. It's a set with no elements whatsoever in here. So writing it looks a bit weird because there's nothing in there. So this is why we generally use this notation. Instead, there's a circle just with a diagonal line going through here. Okay, so we've got these, and there's maybe some things we don't have notations for. Irrational numbers, for example, I've not given you a notation for here. What you can do with that, if irrational numbers are the real numbers except for the rationals. So one way you could write the irrationals to say it's all the real numbers except for the rationals is we say we want all the real numbers. Sorry, pen's working. There we go. And then we do a backslash to say the things we don't want involved. So I'm going to say I don't want the rationals here. So that would be one way of writing the irrational numbers there, and probably the easiest way we've got of writing those. The only other notation I want to mention with sets before we start looking at some operations and then connecting these two concepts is if you're talking about a set A, you might see the notation n brackets A or mod A, and this just means the size of A or the number of elements in A. So that's the number of elements in, and we'll only use that for a finite set. It doesn't make sense to use that for infinite sets there. So those are all the terminologies you need to know specifically to a set. I want to start talking about operations, and like I say, this will connect together with what we've seen with sets. So when we're talking about operations, I'm going to focus on binary operations. This is an operation where you take two inputs and you do something. So not all operations do you need two inputs. If I wanted to reciprocate something, then I'd only give you one input. If I'd only have to say the numbers 5, reciprocate it, and you'd get your output of a fifth. Or I'd say the numbers 2 sevens, reciprocate, you get 7/2. And if I asked you to negate something, you'd only want one input off me to get an output. But binary operations, so that's this, are any operations which take two inputs and give an output. Give one. Sorry, pen's playing up. Give one output. And there's loads of common examples here. The most common are addition's a binary operation because you need to give me two numbers for me to add them together. You give me one output. Subtraction's a binary operation. Multiplication, division. So the most common operations there. Other more complicated examples would be the dot product or scalar product. And if you know the cross product to do with vectors, that's another one. Or let's say you wanted a distance between two coordinates. As we can consider a set of coordinates to be one input and another set of coordinates to be another input, and you could work out a distance between those. So that would be taking two inputs, even though the inputs themselves have two parts to them, that would still count as a binary operation. So those are common ones. We can define strange binary operations though. So I could give an example where I say, well, I just want the binary operation asterisk to represent So if I write A asterisk B, that could mean AB subtract A. So for example, if I was then to say, well, what's 3 asterisk 7? I'd do 3 times 7, subtract 3, and we'd get... Sorry, my pen's really playing up today. And we'd get our answer of 18. So we can define more complicated binary operations in those cases. Now, binary operations can have some special properties, so I'll look at some of those that we need to know. And this is important vocab that you absolutely need to know. The first property I want to consider here is commutativity. So we'll say that, so the operation star is commutative if A star B is equal to B star A. So I'm not limiting my to the example above that, because that example above would not be commutative. If we did 7 star 3 in this example above, then we'd get 7 times 3, 7 star 3, we'd get 7 times 3, but then we'd be subtracting 7, and as you can quickly see, we're going to get a different answer. So that would be an example of one that's not commutative. The most simple examples of something that is commutative are addition and multiplication. Subtraction's not, because 7 subtract 3 isn't the same as 3 subtract 7. Division isn't commutative. So that's one important property that we'll look at. The second one we're going to look at is a little bit stranger, and this associativity. I'm just going to write this down so you know the spelling. So here I'm going to say that star is associative. And it's basically saying whether we need brackets when we're working with this, but I'll give you the full definition here algebraically. So if A star and then brackets B star C is equal to A star B in brackets star C, so it doesn't matter where we put the brackets or not. Again, addition certainly is associative, because if I do 3 plus brackets 5 plus 7, that's the same as 3 plus 5 in brackets plus 7. It doesn't matter where I put the brackets. An example of something that's not associative is division, because if I was to do 3 divided by brackets 5 divided by 7, that would be different to 3 divided by 5 in brackets and then divided by 7. So this is another crucial terminology we need to know and get used to working with. I'll look at some more examples in a few minutes. The final one I want to look at is something called closure. And this requires us to think about sets as well. So we can only talk about closure with an operation in relation to a set. So there's 2 ways we might say this. So we could say that set S is closed under an operation star, or I could say that our operation star is closed on our set S. If what that means is that if we take 2 numbers in our set S and do the operation A star B, so then our answer is still in that set S. So some examples where that would be true. If you think about addition performed on the positive integers, then it's closed, because if you add 2 positive integers together, you'd get a positive integer as an answer. You'd still be in that set of the positive integers. If you did positive integers under division, then that wouldn't be closed, because if you took one positive integer and divided by another positive integer, your answer wouldn't necessarily even be an integer. If we did 3 divided by 4, we're not getting something in that set there. So that's what it means to say whether it's closed or not. I want to look at some more complicated binary operations now, and how we can represent these in tables so that we can start to expand and be able to spot different relations in different forms. So as we start to work with some different binary operations, we're going to want to have ways of storing our results and seeing some of these properties perhaps a little bit more easily. So I want to introduce something now that's called a Cayley table, which is a way of storing our inputs and outputs. And as we do this, you'll realise you've seen some of these as early as primary school, but obviously ones of none of them as Cayley tables. So what a Cayley table does is it lists our possible inputs down a row and across down the column and across the row, and then stores all the outputs in a table. So a simple example I could give you is to say we want to consider addition on just the set of the numbers 0, 1, 2. So we're saying I can take inputs 0, 1, 2, 0, 1, 2, and add these together. And in a Cayley table, the top left is just going to be 0 plus 0. So it's right, that answer would be 0. The next entry would be 0 plus 1. So this answer would be 1. That would be 2. This would be 1, 2, 3, 2, 3, 4. Now, we've already said that addition's commutative and associative. It's difficult to see associativity from this table. In fact, you can't really. There is a property, though, where you can see we have commutativity, and that is that this diagonal here, we have symmetry either side of that diagonal, because it doesn't matter whether I'm doing 0 plus 1 or 1 plus 0, I'm getting the same answer. So it's a nice way to spot commutativity looking at the symmetry along that diagonal. One thing to notice here is that we don't have closure on this set, because we can see that we're getting outputs that aren't in that set. 0, 1, 2, we're getting an output of 4, for example. That's definitely not in our set of 0, 1, 2. So let's consider another example where if we did division on the set 1, 2, 3. Now, if we do that, so again, I'm going to write my entries down here and across here. So my first entry is going to be 1 divided by 1. My next entry here, so on the first row, second column, we're doing 1 divided by 2. It's important with this order here because, as you'll be able to predict, division is not commutative. So this entry here is going to be half. That's going to be a third. Then we're going to do 2 divided by 1 here. 1, 2/3, and then this will be 3 over 2, and 1. So we're getting our entries here. So we already know division is not associative. We've said that. And we already know division is not commutative. How can we see that here? Well, this time we don't have a symmetry in that diagonal. And again, in this case, we can again see it's not closed on this set because we're getting answers which aren't just 1, 2, or 3. We're getting an answer of a half that wasn't in our set. 1, 2, 3. Looking at a more complicated one now and introducing one that you might not have come across before, I want to look at addition modulo 6, and I'll explain what that means in a second, on the set Z6. And when I write Z6, I mean the non-negative integers up to but not including 6. So Z6 represents this here. So I'll do a table to make clear what I mean here. So this addition, unsurprisingly, we do take our answers in that down base, not the final step. So on our table, I'm going to start by putting our entries. I won't do all these because it'll get a little bit tiresome. 0, 1, 2, 3, 4, 5. So 0 plus 0 is 0. 0 plus 1 is 1. This column's exactly the same. What addition modulo 6 means, though, is that our answer, we add our 2 entries, and then we find the remainder when we divide our answer by 6. So if I wanted to find the value going here, I'd be doing 5 plus 3, which is 8, but 8 modulo 6, or if we divide 8 by 6, the remainder is 2. We've got 2 left over. So the entry here would be 2. If we did 5 plus 4, we get 9. That's a remainder 3 when we divide by 6. And then this would be a 4. And actually, we get a nice pattern going on. 5 plus 2 is 7, which is 1. 6 divided by 6 gives us a remainder 1. 5 plus 1 is 6, which gives us a remainder 0 when divided by 6. And 5 plus 0 does just give us 5. So we'd fill our rows in like that. Now, what's nice about these, so I'm going to fill these in quickly because it's a very nice pattern that you should be able to. I would fill this in quickly if my pen was working. Let me just try fixing that. So that's 3, 4. And there's a very nice pattern that goes through here. You can work through that and just check you agree with the answers. but there shouldn't be anything too concerning about these. Now, a few things, I'm not going to write the rest in there. We're getting that symmetry along the diagonal, which isn't surprising because we know addition is commutative. Addition modulo 6 is also commutative. But also, this time, this is closed. All our outputs are at numbers, positive integers 0, 1, 2, 3, 4, 5. So this time, this was closed on our set, unlike the previous examples here. Now, it seems weird that all the examples I've given you so far where we've focused on them, addition was commutative and associative. Division was neither. We haven't really looked at examples where we've got one on or the other. So I just want to mention those examples briefly, and then we'll pause on this video and we'll start to define groups in the next video. So if I give you the operation A star B to be A multiplied by mod B, then quickly pause and consider whether you think this is commutative or associative. In terms of what I'd recommend is, if you're not sure, maybe pick some numbers and try it out straight away. But if you just pick positive numbers here, you might get a misleading idea. We might be able to, one example to show this isn't commutative is to say that if we were to do -5 star 3, I'd get -5 times mod 3, which is just -5 times 3, which is -15. But if I was to do 3 star -5, then I'd get 3 times mod -5, which is the same as 3 times 5, which is +15. So these two things are not equal, so this isn't commutative. However, if whatever numbers you try, you should find it is associative. So I just want to give you a quick proof here that it is associative, because the algebra is not necessarily the nicest, and we'll have a chance to see how this works. So if we were to write A star brackets B star C, then we'd be doing A times, and then we're doing A star, and we're doing B star C. Now, B star C is B mod C here. And then we're doing A star that. So we're doing A times by the modulus of B mod C. Now, that thing is just the same as A times mod B times mod C, because the modulus of B mod C is just going to be whatever B times C is, positive, which we can do by doing the positive of B times the positive of C. Whereas if we do A star B and then star C, the first thing we're doing here is we've got to do the bit in brackets first, as always. So now we're doing A mod B star C, and then what are we doing next? Well, that means that is A mod B times by the modulus of C, which is exactly the same here. So we can see now it's associative, even though this wasn't commutative. So there's an example there. If you want to see an example, I'm not going to go through it, but it's a chance for you to check for yourselves. An example of something that's not commutative, if I say A circle B is equal to AB subtract A subtract B, you should quickly be able to prove that this is commutative, but it's not associative. So try doing that. Associativity, it might be easy if you just try some numbers, and you'll quickly see that, for example, 3 circle brackets 5 circle 7 isn't the same as brackets 3 circle 5 circle 7. But give it a go, try it out. This is an example of one that's commutative but not associative. Next video, we'll start to define groups and we'll get properly into the group theory. Thanks very much.